Okay, here's the starter. So pause your video. To do this, you do need to have done Maths Lesson 41, the starter, but not, you don't need to have done it to do the lesson. So, okay, they're the answers. Right, what we're going to do today is we're going to look at Standard Maclaurin series. Now these are, you've got a few standard functions that are going to be given to you in your formula book, and it means when you're allowed to use these and the question will be quite clear, then you can just substitute a value in. It makes it much easier than what we were doing last lesson. So you can see you've got 1 for e to the x, ln 1 plus x. Now this is the most awkward because that has to be 1. It's a little bit like the binomial, and you have a condition that x has to lie in for this to be valid. Sin x, cos x, and here this one is like your binomial. So that's what it looks like. So example 1, use the Maclaurin series for cos x, there it is, to find the first 4 terms in the series of cos 2x cubed. So you're going to replace your x with 2x cubed. So that's what it's going to look like. Replace the x in here with 2x cubed, and now just simplify it. Looks like that. Looks like that. So you're just shoving 2x cubed into this and then gathering the terms together. Now you can see that cos x is valid for all x. So all x, or x, is a member of the reals. Straighten that up. Right, example 2. Use the Maclaurin series for e to the x to find the first 4 non-zero terms in that expansion, e to the 2x. So you're literally going to replace the x with 2x. The issues here, it only goes up as far as the squared term, so you know the next one will be x cubed over 3 factorial. So you replace all those x's with 2x cubed and then you work them out. There's your answer. Example 3, slightly harder. E to the sin x as far as x to the 4. Now, sin x pretty quickly gets beyond x to the 4, so you're only going to be interested in those 2 bits there. So e to the sin x gets written like that. Using laws of indices, you can split it up. That now becomes an approximation because you've truncated it, you've rounded it. You're now going to expand these both separately using your e to the x expansion and then multiply them. So it's going to look a bit like that. You're now going to expand these, so multiply everything by 1 and then everything by x cubed over 3 factorial. But as soon as I get beyond this term, I'm just going to start getting x to the 5s, so I don't bother with that anymore. And then I gather them together. So there's my answer. Now, e to the x and sin x are valid for all x, so this expansion is valid for all x. Okay, here are your questions to do. So if you pause the video, do those questions. Take your time. You're using these series expansions. Okay, here are the answers. Right, expansion of ln 1 plus x to the power of n. Now that only works if there's a 1 there. So you've got to be mindful of that. So using this to expand ln 2 plus x, what I'm going to do is I'm going to take out a factor of 2, but of course I can't take it outside the ln. So I rewrite it as ln bracket 2 bracket 1 plus x over 2. You can see I've taken out a factor of 2 just from the 2 plus x. Then using laws of logs, the log of a plus the log of b is the log of a times b. I've worked backwards and I've split up that product. So I've now got ln2 as my first term, and I'm now going to replace, because I've got the 1, I now can replace this x with an x over 2 into this expansion. So it looks like that. And now I simplify it. And I know that whatever went into this expansion, that is less than or equal to 1 and greater than -1. So multiplying all through by 2, I get my condition of validity. Okay, if you can try this question using your ln expansion. So pause the video, try that. And there's your answer. Right, harder example. Find the first 3 terms of the series for ln 2 minus 3x. Now you know you can't use your expansion there, so you're going to have to take out a factor of 2. So there's your expansion that you're going to use. So taking out a factor of 2, and right, they're writing it a bit neatly there to make it easier to spot what you've got to substitute. And then using laws of logs, that becomes ln2 plus ln1 plus minus 3 over 2x. You're then substituting, so your ln2 is now your first term. Substitute minus 3 over 2x into this expansion. And now all you're doing is a bit of simplifying. Make sure you can see what we're doing there. Okay, now part B, it then asks you to find the Maclaurin series up to x cubed for this. So the first thing we're going to do is use laws of logs to separate that. You know, ln of a over b is ln a minus ln b. Now, you know, I just wrote that there because they cut a corner, that the ln of the square root of 1 plus 2x is ln of 1 plus 2x to the half. So that half can come down to the front of that log. So that's why we get a half ln 1 plus 2x minus ln 2 minus 3x. I'm going to get rid of that because it looks really bad. It's gone bad in your notes. Now, this first bit, you're going to be able to expand using your ln expansion. And the second bit, you've already done. So this first bit, you're going to expand by replacing x with 2x in here. So it's going to look like that. So this is just looking at this first bit. So it looks like that, multiply by a half. And then you're going to subtract this bit that you got in part A. So you're then going to subtract the bit that you got in part A. So you're going to do some simplifying there. So multiplying everything there by that takeaway. So you end up with that rather ugly looking thing there, leading with a minus ln2. And lastly, if you remember what part C was, we go over the page here, state the interval in which the expansion is valid. Right, well, this is going to be all about the ln, isn't it? So if you have a quick look here, you know 2x will have to lie between 1 and -1, not equaling -1. And in this one, minus 3x over 2 will have to lie between 1 and -1. So let's have a look how that pans out. So for your first bit here, that's multiplying all through by